Good day, everyone. My name is Sarasna M. Kamen, and I am going to talk about the graph algorithm, topological sort, and Hamiltonian tools in this video. So let's start with a basic introduction of what graph is. So, by the definition, when we say graph is an abstract notation used to represent the connection between pairs of objects. And a graph consists of vertices and edges. When we say vertices, it's also commonly known as the nodes, which is interconnected objects in a graph. And the edges is commonly known also as the arcs, which is links that connect the vertices. In this simple diagram, it shows the vertices connected by the edge. So we have vertex A here and a vertex B here that connects through an edge. So this is what we call the edge, and A and B here is what we call the vertices. Next, there are two types of graphs. First is the directed graph, and second one is the undirected graph. When we say directed graph, are also commonly known as a digraph, which is have a pair of ordered vertices u, b. When we say ordered vertices, means that the order of appearance of the vertices in a set matters. Means u, v, which is a, b, is not equal to v, u, which is b, a. While in the undirected graph, which have a pair of unordered vertices, u, v and v, u are the same. For example, we have u, v, which is a, b, and v, u, which is v, a, are equal. So you can see the difference between this diagram and this diagram. So in directed graph, we have an edge which is directional, while in the undirected graph, the edge don't have a direction in it. So which means that the relationship between these two vertices hold in a both direction. And now, here's some application of a graph. A graph are used to solve many real-life problems. And also graphs are used to represent networks, which the networks may include paths in a city or a telephone network or a circuit network. And also graphs used in social networks like LinkedIn and Facebook. So for example, in Facebook, each person is represented with a vertex or what is commonly known as the node. Each node is structured and contains information like person ID, name, gender, and local. So next is, let's go to the graph representation. So there are two ways to represent a graph data structure. First is the adjacency matrix, and second one is the adjacency list. So let's proceed first with the adjacency matrix. When we say adjacency matrix, it represents graph with V nodes into an V times V 0 minus 1 matrix where Aij is equals to 1. Means that the vertex I and J are connected. And take note that the V here, it refers to the number of vertex a graph has. So, if we say that I in a row and J column is 1, means that there is an edge between 0 and 1. So let's take an example. Here. So the graph is undirected graph. And we have 5 vertices here. We have a vertex A, vertex B, vertex C, vertex D, and vertex E. For short, we have a vertex A to vertex E. In this example, it corresponds into this what we call the adjacent matrix. So, how it came up with this? All zeros here in the matrix means that there is no connection between two vertices. For example, A to B. A to B is equivalent to 1. It means that A and B here have a connection. While A to D, let's see, A to D, A and D here, which is equivalent to 0, means that A to D has no connection. So as you see here, that the adjacent matrix corresponds to the connection of vertices in our undirected graph. And the graphs do not contain any self-loop. What do we mean by that? Because A has no connection with its own self. So that's why vertex A to vertex A has a 0 value here. It means that there is no connection. That is what we call the self do not contain a self-loop. Well, A to B, it's like as what I said, A and B has a connection. Then A to C has no connection, as we see on this graph. There's no connection between them. And A to D also has no connection here. That's why it's 0. And A to E here, which is A to here in the graph has connection. That's why the value here is 1. When we say B to A, it has a connection. That's why it's 1. And B to B, that is what we call self-loop. Therefore, there is no connection within that. Then B to C, which is have a connection. That's why it's 1. And B to D here had a connection. That's why 1 here. And B to E, it has a connection. B to E, so in this graph, it has a connection. C to A, it has no connection. C to B, it has a connection. C to C, self-loop, it has no connection. C to D, it has a connection. C to E, it has no connection. D to A, it has no connection, but D to B, it has a connection. D to C, it has connection. D to D, which is self-loop, it has no connection. And D to E, it has a connection. And that is E to A, E to B, it has connection. It's also with E to D, it has a connection. It has no connection only to E to C and self-loop. So that is what we call the adjacency matrix. Let's go to the second graph representation, which is the adjacency list. When we say adjacency list, it is an array of linked lists is used. Size of an array is equal to number of vertices, and each entry of array corresponds to a linked list of vertices adjacent to this index. So it means that adjacency list uses an array of linked lists to store a graph. So let's take an example. So we have here an undirected graph with 5 vertices. Vertex A, vertex B, vertex C, vertex D, and vertex E. And with this graph, it represents into adjacent list like this. Okay, how it works? We have here the vertices A, vertex B, vertex C, and vertex D, and vertex E. Vertex A here, and let's see which vertex they are connected. Vertex A is connected with B. That's why A is connected with B. And also vertex A is connected to E. And only that. While V, which is vertex A, is connected to A. That's why connected to A. And V is also connected to E, and connected to D, and connected to C. And vertex C is only connected to B, and it's connected to D. That's why the vertex C here is connected to B, and it's connected to D. And D here, the vertex D here, is connected to B, connected to C, and connected to E. That's why in the adjacent list here, you can see that D is connected to B, and it's connected to C, and it's also connected to E. And last one is the vertex E. As you see, vertex E is connected to vertex D, vertex A, and it's connected to vertex B. So in here, you can see that vertex E is connected to vertex D, vertex A, and vertex B. And this is the adjacency list. And this is the corresponding adjacent list of this undirected graph. And now, we're going to discuss about the topological sort. So in a directed acyclic graph, or DAG, topological sort is a linear ordering of vertices such that for every directed edge, u comma v, vertex u comes before b in the ordering. Let's define first what is directed acyclic graph. So directed acyclic graph, or the DAG, is a graph that is directed and without cycles connecting the other edges. So this means that it's impossible to traverse the entire graph starting at one edge. The edge of the directed graph only go one way. So the graph is topological sorting, where each node is in a certain order. So given a directed acyclic graph, topological sort is a linear ordering of its vertices, such that for every directed edge from vertex u to vertex v, u comes before b in the ordering. Let's take an example. So this is a sample of directed acyclic graph. So we have 5 vertices here. We have vertex A, vertex B, vertex C, vertex D, and vertex E. So topological sort is not unique. The topological order for this graph can be one of this. It means that we can start at vertex A, going to vertex B, going to vertex C, going to vertex D, and vertex E. Or we can start with vertex A, then go to vertex C, then go to vertex B, then go to vertex D, then vertex E. Let's look into details of how a topological sort really works. Now, let's learn topological sorting through an example of this graph. Consider this directed acyclic graph with vertex A to vertex J. So first thing is, let's have an empty stack. And we initially have all these vertices as unvisited, as shown by this color marking. This one is unvisited and this one as visited. And now let's begin with the vertex A. Since vertex A is unvisited, so we are good to go. So now we're going to mark vertex A as visited. Then, we're going to look on the neighbor of vertex A, which is the vertex F and vertex B. But, we'll choose alphabetically. We are going to choose the vertex B. Now, we're going to mark vertex B as visited. And we move to its unvisited neighbor H. And mark H as visited. Since there are no unvisited neighbor of H, we're going to push H into our stop. And go back to our vertex B. Since we see that the vertex B also have no unvisited neighbor left. Therefore, we're going to push B into our stop. And move back to vertex A. Now, vertex A has its unvisited vertex, which is vertex B. So, we're going to visit this F by marking this one. So, since F has no left as unvisited neighbors, Therefore, we're going to push vertex F into our stop and move back to our vertex A. But since vertex A has no left unvisited neighbor, therefore, the vertex A must be pushed into our stop. So now, we're going to start with another unvisited node. So we choose the vertex C and visit it. Since there are no neighbors of vertex C, so we push vertex C into our stop. And we again start with the vertex D. Visit it and we move to its unvisited neighbor, which is the vertex E. So, the vertex E must be visited now. Then, we move to its neighbor I, which is unvisited. And we're going to mark I as visited. So, we push I because we push I into our stack because there's no left other unvisited neighbors. And we go back to vertex E. Since vertex E has no left unvisited neighbor, so we also push E into our stop. And go back to vertex D. And now, vertex D has no other unvisited neighbor, so we also push it into our stop. Now, we're going to choose again unvisited node or unvisited vertex. So, let's go and visit vertex G. Since all its neighbors are already visited, so we push G into our stop. Then, lastly, we choose the vertex J and visit it. Since all its neighbors of vertex J are already visited, so we push it into our stop. Since all the vertices of the graphs are already visited, now it's time to print the content of our stop. Which is, it must be printed like this. So this is how our topological ordering be for this graph. So we have J, G, D, E, I, C, A, F, B, and H. Now, let's proceed to Hamiltonian. First of all, there's something called the Hamilton path, then Hamilton cycle. When we say Hamilton path, it is a simple path that visits all the vertices of the graph exactly once. And when we say Hamilton cycle, or commonly known as the Hamilton circuit, it is a simple cycle that visits all the vertices of the graph exactly once. So let's do an example. Let's have an Hamiltonian path. In Hamiltonian path, it's okay not to visit all the edges of the graph as long as you're going to visit all the vertices of the graph at exactly once. So let's start from the vertex A to vertex B. Then next, we'll go to vertex I, then continue to vertex H, then let's go to vertex C, then continue to vertex D, and go to vertex E, then go to vertex F, and lastly, we go and ended with the vertex G. So as you see, in this graph, we visited all the vertices of the graph. It's not necessarily we need to visit all the edges of the graph. The important in Hamiltonian path is that you need to visit all the vertices of the graph at exactly one. We can have another path. We can start at vertex A, going to vertex I, going to vertex B, going to vertex H, going to vertex C, going to D, going to E, going to F, going to G. We can have also another path. We will start at vertex A, I, H, then go to B, going to C, going to D, going to E, going to F, and ended with G. There are many paths that you can do in Hamiltonian path on this graph. The important thing in Hamiltonian path is that you must visit all the vertices of the graph at exactly once. Next, let's go to Hamiltonian circuit. In Hamiltonian circuit, it's like a special type of Hamiltonian path. It's a Hamiltonian path that starts and stops at the same vertex. It means in Hamiltonian circuit, if you start with a vertex A, you must end or stop at the vertex A. Let's have an example. So let's start with a very simple example. So we have three vertices. We have vertex A, vertex B, and vertex C. So let's start with the vertex A, going through to the vertex C, then C to the vertex B. And it must be ended with the same vertex where you started, which is vertex A. So B to vertex A. So this is a sample of a Hamiltonian circuit graph. So let's have another example. This graph. So we have four vertices, vertex 1 to vertex 4. So for example, let's start with vertex 1, going to vertex 2, then going to vertex 3, then going to vertex 4, then ended at the vertex 1. Or we can have another path for that. We can start at vertex 1 to 3, then vertex 3 to 2, then go to vertex 4, then we ended with the vertex 1. So that is a sample of a Hamiltonian circuit graph. What is the difference between Hamiltonian path and Hamiltonian circuit? When we say Hamiltonian path, it's simply you must visit all the vertices of the graph at exactly once. While Hamiltonian circuit is that you must visited all the vertices at exactly once and ended with the same vertex where you started. And that's all. Thank you for watching this video tutorial.